All right, lesson 110, another math involved lesson here. But again, very important, very relevant. So we're going to talk about voltage drop here. So we're getting into a little bit of tough math. I don't think it's too bad. So first question, what is voltage drop? What are we talking about? Why do we have this? So voltage drop essentially is as the name implies, when we actually end up with fewer volts at the load than we started with at the source. What causes this? Well, essentially excessive resistance in our conductors, right? High resistance could be caused by a few things here, but essentially when you have high resistance, your conductor almost acts as a heating element, right? Heating element has very high resistance, which it restricts the flow of electrons. It heats up. To a very small degree, your conductor can do that, and sometimes not to a small degree, to a large degree, but even in a small way, your conductor can actually act as a heating element here. So again, think of your water going through a kinked hose or something like that. We've all seen that that kind of thing happen. It's kind of the same thing in an electrical point of view here, right? So what's going to cause this? What's going to cause our conductor to have excessive resistance? A very long conductor, okay? It doesn't necessarily mean you did anything wrong, but maybe there's just a very long run of wire that's inevitable. That can cause excessive resistance. High ambient temperature, that's why we just talked about in the last lesson your derating factors for high ambient temperatures. How do we combat that? We run a bigger wire, right? So high ambient temperature means your molecules expand. It's harder for electrons to go from one to the next, therefore you get a higher resistance. If you have a conductor that's just too small, again, we looked at the derating factors and the answer everywhere was run a bigger conductor. Well, that's the answer here too, to combat voltage drop. And I don't think I mentioned it here, but poor connection is another one that the book's going to talk about. That can do the same thing. So how do we how do we figure voltage drop? Well, before we do that, we need to introduce a new term here, and that's circular mill area. We already talked about KC mill and a little bit on the from table 31015 B16, but we're really going to get into looking at that and talking about how we determine that. So a new table we need to look at here is going to be table 8, conductor properties. Okay, so we didn't talk about chapter 9 too much in the code book, but chapter 9 is where several tables are going to reside. So that's towards the back of your code book. Chapter 9, Table 8 specifically is what we want to look at. You're going to find that on page 689. I would encourage you to take a moment to flip to that page in your code book and follow along. So Chapter 9, Table 8, if you hear me reference that, this is what we're talking about. So there's a few things we need to look at here. In particular, there's a lot of stuff on this. So we have conductor size here, again, an AWG or KC mill. We're particularly interested in this circular mills column for voltage drop. That's the one we're going to be looking at here. Some other things I think are worth mentioning is it actually tells us, so we have this section here is for stranding. So this will tell us quantity. How many strands do we have? That'll actually tell us the diameter of each individual strand, right? And then here we have overall, where it'll tell us the overall conductor if we ever need to know the diameter of them. And, but again, we're really looking at this circular mills column. I find this interesting, but I've never found it entirely helpful. So, again, we're going to look at our size in AWG or KC mill as it relates to the circular mill. We're going to need to use the circular mill in our voltage drop formula. Okay, but what about, these guys down here at the bottom? So if you didn't see that, we're talking about these ones from down here at the, getting my head. So these ones down here at the bottom that don't sort of have any circular mill listed, what's the deal with that? Well, again, remember KC mill means thousands of circular mills. So a 250 is literally 250,000 circular mills. A 500 KC mill is literally 500,000 KC mills. So they just simply didn't list it there. We can basically add 3 zeros to the wire size. There you go. You don't even need to check the table. So formulas. We have 2 voltage drop formulas that we are going to worry about. There are a lot of different ways to go about this. This is really the only way that I recommend. It's all I've ever done. So first formula is this guy, and then second one is this one. Notice the only difference is we flip the number to the value to the left of the equals for the denominator here, right? We just simply flip-flop these two numbers. Why two equations? We use this first one if we know the wire size, but we don't know what our voltage drop is going to be. And we use the second one if we know this is what we are going to allow our voltage drop to be, what size wire do we need to run for this. So again, you kind of use this one if you maybe you already ran the wire. You say, oh, we might have a voltage drop issue. Let's see how many volts we're actually dropping. Versus this one is a little more, proactive, saying, hey, what size wire should I run if I know my voltage drop can only be this? So let's look at these values in a little more detail before we get too far down the road here. So our first value, ED, is volts dropped. That's just going to be simply a number of volts dropped. So we're going to drop 7 volts, 8 volts, 9 volts, whatever that is. That's pure and simply the number of volts that are dropped in the situation. CMA is your circular mil area, or in other words, your wire size. K is going to be a number that represents the conductivity of your material. A couple references will tell you that 12.9 is the K value for copper, 21.2 is the K value for aluminum. A lot of times your textbook will give you a K value. If they give you a K value in the problem, go ahead and use it. If they don't, these are going to be what you're going to want to use for your K values. Letter I is going to be for amps. We should be familiar with that by now. L is going to represent length of the circuit, overall length. And then lastly, we're going to use the number 2 if it's a single phase circuit. If you're looking at a 3-phase circuit, you're actually going to use 1.732 instead of 2. That's a common number when you deal with 3-phase voltages. You're going to do a lot of that in year 2 and 3 and 4, not so much in year 1. But it's actually the square root of 3, 1.732. All of our examples we're going to look at today are single phase, so we're going to use that number 2. All right. So let's talk a little more about the voltage portion of this, the volts drop. So generally 3% is a good allowable voltage. We're going to allow up to 3% voltage drop. So if we're looking at a 120 circuit, 3% of 120 is 3.6. In other words, if we lose 3.6 volts, we're at 116.4. So I'm okay if I'm there or above. Same thing on 208, we drop 6.24. In other words, 201.76, so on and so forth. You can see, and I'll go ahead and just work this through all the way up to 480. If you want to sort of jot this down or figure it out, because you're going to find yourself doing these calculations several times, it may be good just to jot this info down in your notes somewhere, right? So let's do an example here. So in this case, let's say we have a 120 circuit with copper wire, 12 amp load, 215 feet long, single phase circuit with number 12 THHN conductors. Okay. So we have our first formula here if the wire size is known. We have the second formula if the voltage drop is known. I look at this, okay, I do know the wire size. I don't know the voltage drop yet, right? So we're going to scrap this one and we're going to use this first formula. And the way you can tell whatever you're looking for, whatever is unknown, is going to be on the left of that equal sign. In this case, it's voltage drop. So let's go ahead and fill in some values here for our equation. So our K value is copper, so it's 12.9. We have a 12 amp load, as we said, it's 215 feet long, and it's a single phase circuit, right? So now we got to do the CMA down here. How are we going to get that? We have to take our number 12 THHN conductor. Let's pull up chapter 9, table 8. We're going to see here that a number 12 actually has 6,530 circular mils. So that's the value we're going to plug in down here, 6,530. So keeping order of operations in mind, I'm going to have to basically do this top section of this equation first, multiply that through. Then we'll go ahead and divide these two out. And we're going to find out that our voltage drop is 10.194. So in that circuit, we're going to drop 10.194 volts. So in other words, we are only going to have 109.806 volts at our source. If we go back and reference, I said if we're keeping the 3%, I don't want to go below that. So we would have an issue with this. We would have to upsize this wire in order to alleviate voltage drop. So anyway, we've just determined we're going to drop 10.194 volts, or the load is going to see 109.806 volts. Okay. So let's look at the other way around here. Do another example. In this case, we have a 240 volt circuit, aluminum wire, 22 amp load, 150 feet long, single phase, and we're going to allow 3% voltage drop. So what's the difference here, right? Well, which formula do we want to use? We know that we want to go ahead and use this formula here, right? Because we don't know what our wire size is. I do know, I said 3% voltage drop is allowed. So we know what the voltage drop is going to be, or we can figure it out here pretty quickly. So we're going to use this version of the formula, right? So let's go ahead and fill in some values here. So my K value is 21.2 because we're using aluminum wire. 22 amp load, 150 feet long, single phase, so we use multiplier of 2. So what are we going to put in here for our voltage drop? Well, I told you it's a 240 volt circuit. We're going to allow 3% voltage drop. What does that work out to be? 7.2. So again, back to that slide I showed, I said you might want to jot that down. You could have already had that in your notes. Again, it's easy enough to figure out. So we have a complete equation. Let's go ahead and again do the top part. Let's multiply across, and we come out with this. Now let's divide these guys out, and we end up finding that our CMA is going to have to be 19,433 and some change. Okay, so how do we change that from CMA to an actual wire size? Let's go back to Chapter 9, Table 8. We're going to find out here that our number 8 is actually not quite big enough. However, our number 6 is going to be big enough. We have 26,240 CMA, and we actually only needed 19,000. So once again, your number 6 is going to do the job for us in this case. So that tells us if we run a number 6, we will have less than 3% voltage drop. That's probably the most common version of this formula. It's definitely the most helpful, most productive. But you will see a decent mix of either formula, so try to get used to using either. Biggest thing is knowing you check Chapter 9, Table 8. You can go from CMA to AWG wire size and vice versa. Okay, so there's your voltage drop lesson.